Hi, I'm Brian, and in this science review video, we're going to be taking a look at one of the more intimidating topics of the physical sciences on the MCAT, magnetism. In doing this, we're first going to evaluate the characteristics of magnetic fields, and then move on to categorizing the different types of magnetic materials. Afterwards, we'll analyze how current-carrying wires create magnetic fields before we evaluate the way those magnetic fields affect moving charges. The end goal of this lesson will be for us to be able to recognize the cause and effects of magnetic fields. I want to acknowledge that magnetic fields are 1. Cool, but 2. They can be challenging to conceptualize, and that's something on which we want to focus today in order to allow us to answer questions like the one at the bottom of your screen asking about the magnetic field created by any given current. The necessary first step in attacking magnetism is looking at magnetic fields. Magnetic fields are created by magnetized objects and any moving charges. In fact, magnetized objects only have magnetic fields because of the moving charges within them. The field created by those moving charges is often represented by magnetic field lines. This is very similar to the electric field in that it is a field force that permeates space. It causes movement of charges. Other magnets placed within the field will align with those field lines so that south and north always point at one another from one magnet to another. To measure magnetic field strength, we use the unit the Tesla. Another unit of magnetic strength is the Gauss, which is much smaller than the Tesla, as the Tesla is 10 to the 4th Gauss. And just like electric fields, the charge that creates the magnetic field is not affected by its own field. These fields that are created by the magnetized objects and moving charges will have the same type of symmetry as the source that causes them. For instance, a plane will have symmetry along the same lines as that plane, and a cylinder like a wire will have the same rotational symmetry as that wire does. As I just mentioned, those magnetic field lines created by the moving charges and the magnetic objects are very similar to electric field lines. This is true in that they are able to visually represent both the strength and the direction of the magnetic field at any point in space around the object. For direction, arrows within the plane of the page will just point in the direction of the magnetic field. Here we see a magnetic field with arrows pointing to the left, indicating a magnetic field to the left. However, that magnetic field can go in or out of the plane of the page. When it goes into the plane of the page, we use X's to represent it. We can think of this as an arrow going into the page, and we are looking at the cross made by its feathers. Or if the magnetic field is coming out of the page, it is represented with circles and dots. These represent the points of the arrow coming at us. When we draw magnetic fields around a permanent magnet, we represent the field lines exiting from the North Pole and seeking the South Pole of the magnet. When you put North Pole near North Pole, because they do not want to go to one another, this is what causes the like poles to repel. On the other hand, if you put a North Pole near a South Pole, those magnetic field lines are able to go straight from one to the other, from north to south, and that causes them to attract. And once again, just like electric field lines, we can see that the greater the density of magnetic field lines, the greater the strength of the magnetic field. And also, like electric field lines, these lines will never cross one another. This is because they are vector sums and add up the net magnetic field from all local sources. At no point could we have the net magnetic field pointing both right and up. So we would have to take the vector sum and have an up and to the right magnetic field, for instance. Now it's time to see how those magnetic fields interact with magnetic materials. When I say magnetic materials, it kind of sounds like I'm talking about this or that specific material that has magnetic properties. But what I'm really talking about is all materials and their specific magnetic properties, because all materials can be classified into one of 3 categories of magnetism. The first are the diamagnetic materials. These materials are weakly repelled by external magnetic fields, and the resulting magnetic field produced within the material is temporary. And if we look at any examples, for instance zinc, we can see that they have nothing but paired electrons. So every electron in the material is paired, and these paired electrons exert that force that slightly opposes the magnetic field. When we're looking for diamagnetic materials, they're basically anything that we think of as non-magnetic. Wood, skin, all the materials we conceive of as being non-magnetic are in fact diamagnetic. The next category are paramagnetic materials. Paramagnetic materials are weakly attracted to those external magnetic fields, and like diamagnetic materials, the effect is temporary. This is because they have some unpaired electrons. As we look at titanium, we can see that it has unpaired electrons in its 3D shell. These unpaired electrons align with that applied magnetic field, making for a slight force of attraction. And the third category are the ferromagnetic materials. These are materials that can become magnetized and stay magnetized by an external magnetic field. The reason they can be durably magnetized is because they are similar to paramagnetic materials in that they have unpaired electrons, but their magnetic field, once generated, is able to persist because of specific electron configuration properties within these materials. Now, this is true of a limited number of materials, and these are the materials we typically think of when we're thinking of magnets. To remember which ones they are, you can remember that iron filings on a magnet resemble a pine tree, and pine trees are conifers. And the three major ferromagnetic materials are cobalt, nickel, and iron, Fe being the atomic symbol for iron. One way of creating magnetic fields is through a current-carrying wire. This is the way we make electromagnets. So we want to keep in mind here, thinking to some knowledge of circuits, that when we're talking about the movement of charge through a current-carrying wire, we're talking about the flow of positive charge. This is opposite of what is happening in terms of the actual flow of electrons, but we will define conventional current in this way as a convention that was set hundreds of years ago by Ben Franklin. To measure current, we use the ampere, which is equal to 1 coulomb per second, where coulomb is our unit of charge measurement. To illustrate the movement of conventional charge, let's look at a negative charge like an electron moving through a wire. Here we see one moving downward in the screen. So that would be what we would typically think of as actually happening. But when we're talking about conventional current, we're talking about the movement of equivalent positive charge. So it would be moving upward in this case. This is one convention we definitely want to have in mind for test day. There are two types of wire we can look at when we're looking at the way that magnetic fields are created by current. The wire can either be in a straight line, or it could be going through a circular loop. The Biot-Savart law describes that magnetic field for whichever configuration. As we look at the example straight wire on the left, the current moving upward in the screen would create a magnetic field that circles around counterclockwise if viewed from above. And the Biot-Savart law would describe the magnitude of that magnetic field at any given distance r from that wire. On the other hand, if we look at the circular loop of wire, and in this circular loop current is going counterclockwise, that would lead to each point along the wire creating a magnetic field in the same way it's created by the straight wire on the left. But those successive magnetic fields created by the different points along the circular loop all overlap in the middle to create a magnetic field at the center of the loop that is coming out of the page. At that point in the center, with r now being the radius of the loop, we have the other version of the Biot-Savart law, which describes the magnitude of the magnetic field there in the center of this loop. One way or another, we can recognize that the magnetic field strength is inversely proportional to the distance from the wire. So the larger the r, whether the farther away you are from the straight wire or the larger that circular loop of wire, the weaker the magnetic field will be at this point. We also see mu naught appearing in this equation, and that mu naught is the permeability of free space. This is equal to 4 pi times 10 to the negative 7. Now this can all seem daunting, but this is where the first version of our right-hand rule comes into play. The right-hand rule will help us determine the direction of the magnetic field in relation to a straight or a circular loop of wire. When using the right-hand rule, make sure to put your thumb in the direction of positive charge movement, the direction of conventional current movement. So if you are thinking of the electrons moving through that wire, you want to point your thumb in the opposite direction, in the direction of conventional current. Then you grab the wire. Note, don't grab live wires. As your thumb is in the direction of conventional current movement, as your fingers are grabbing that wire, they will wrap around the wire in the same direction as the magnetic field. This works in the same way for the circular loop of wire as the straight wire, and in the circular loop of wire you will be able to determine whether the magnetic field is into or out of that loop of wire by the way your fingers wrap when you grab the wire with your right hand. In terms of the Biot and Savart laws, there is a nice way to remember these equations. When we're looking at the circular wire, there is a donut-shaped magnetic field created, or even just the circular loop of wire can be considered a donut, whereas the straight wire has pi in the denominator, and you only get one dessert. If you take the donut, you don't get the pi. So the circular loop of wire creates a magnetic field that you calculate without pi in the denominator.